Part 7, Design Examples. Finally, we can take a look at some design examples that should fix in your mind, at least help you better understand practically what we did in the last lecture parts. We will start by introducing our integrated development environment of choice, which is going to be the STM32CubeIDE. Then we will go with a demo of a simple alarm clock, and we will move to a command line interface example using a Uart communication. After that, I will show you a relatively simple example I made recently that works. I know it works, and first of all, and secondly, it uses pretty much all of your analog part of your microcontroller, meaning that and you will be able to use it also with just your board. So I think it's a nice example in this case. Finally, last but not least, we will introduce how to use the libraries inside the STM32CubeIDE provided by ST, with a specific example with Bluetooth low energy programming. What is the STM32CubeIDE? It is free. I don't know if it's open source, but at least it's free. In the integrated development environment for development, especially for the microcontrollers provided and sold by ST Microelectronics. It is compatible with a wide range of microcontrollers, all based on the ARM architecture, meaning that pretty much all of their microcontrollers will be compatible, but there could be some exceptions, of course. For instance, the microcontrollers in the series of Blue Energy 1 and Blue Energy -2 will not be compatible directly with this software. You will eventually have, for that specific case, you will have to use external other software provided by other sources, but the flow, in any case, the flow of your design flow and your programmation flow should not change too much. A good thing about this IDE is exactly the cross-compatibility with a wide range of operating systems. It will work with your Windows PC, with your Mac OS, and your Linux computer also. So, from this point of view, it is pretty interesting. It has all the basic features you will want from this kind of development environment, like programming, debugging. Eventually, you can even access to some extras, like that we will see soon. Like, for instance, one cool example is the access on machine code of your specific device. Okay, so you can see which instructions actually correspond to what you want to do. Let us go. I will show you immediately the STM32CubeIDE software. I have already installed it here, of course. Okay, I think I'll do a cut here eventually. you can download the software from the link here provided, and I have it already installed for of course. So I will launch it immediately. You can see that you have the first thing you will see actually is a window asking you which workspace to use. Ideally, a workspace is a folder that will contain most, if not all, of your projects that at the very least should be inside the same category. It is not mandatory to put everything on the same folder, on different folders, on different, same workspace or different workspaces. Actually, it could be fine. I mean, but this is a tool that you have provided basically for organizing everything, which is pretty cool. We will start by creating a fresh workspace, just to show you what you will find, of course, in the beginning. I will call this one new workspace. I know it's a very special, like imaginative name, I guess. Let's launch it. Okay. First thing you will see is that, yeah, it is not opening the very prettiest way, but you will see pretty much this interface. I guess it is better to close this because, I mean, you can use these buttons here, but we will use actually this side. So let's close. So what we will do now is gonna be the same I mean, it's gonna always be the same, okay? All right, so what we can do here now is maybe create a new STM32 project. Depending on which board you have with you, if you do have one, of course, you can select the board from a special board selector that will load all the download and load and configure all the necessary libraries in order to make everything work more or less flawlessly. In my case specifically, I do have an STM32 L476RG on a Nucleo board, so it's a Nucleo-L476RG. If you have a custom board, you will eventually want to select a microcontroller through this interface, particularly like select this one, for instance, then go next, etc. Of course, it is not our case, but I can show you some features here that you might find actually pretty useful. Here you can select, you can basically choose within all of the available microcontrollers, you can choose which ones you can like divide them by features. Let's say you do need like 2 low power timers, for instance, okay? If you do know that, you can go on the timer and see low power timers. Okay, let's go start from 2 low power timers. You see that the list here like decreased a lot in number, of course, of elements, from 3000 to 1000. Then you can also do the same for different characteristics. You can do that for the RAM, you can do that for interfaces, that USB interfaces. You can do you have a lot of choice here, you can see. Let's say that you find interesting, for instance, this one, H7, like the first one that came, that I clicked basically. You can see here on up here, you can see several other informations, more specific information about the hardware here, some block diagram of what you have inside. Document, you have quick access to all of the documentation, which is very, very, very important. I cannot stress this enough. I will begin stressing this starting now, actually. Read your documentation, because of course, if you can read your documentation, let's say that you are like halfway through your job, basically. You will probably pass a lot of time reading that, but that is time that is actually saved from when you have to find things. As you could see before, here I click the datasheet, and in this case it sent me directly to the datasheet from the ST website, and I have it downloaded already. It's 200 pages that you will probably want to read all, probably not, but it's good to have it nearby, of course. Of course, if you have a specific board like what I said here, you can select it in the board selector section. You can, for instance, search it from here. In that case, I have, say, the Nucleo L476RG, and there is only one, of course, in this case. There are no multiple boards with the same name, which is good, I guess. You can see the price here also. It's not super expensive. And I advise, if you are planning to use this, whatever board you have, multiple times for exercise, etc., to click this small star here. Usually it's white. When you click it will become blue. And you will see that this button will become accessible if you already have at least one board selected. And the cool thing is that if you don't write any information here, you can still click the star and it will give you directly your board. Okay, it will save you like 1 minute or a couple minutes. But yeah, maybe it's not a lot of time, but it will save you some annoyances. Here we can finally write our name for the project. I can write, for instance, test PRJ or project. Let's do 1. And here you have other possibilities of choice. You can say, okay, I want to work in C++. In this case, we will do in C. The library type, etc. On next, you have a choice of the reference firmware package and so on. Or eventually, on most cases, you will just want to click finish, and that will be fine. Initialize, it's gonna ask if you want to initialize everything in the default mode. Of course, the answer is yes, initially at least. Do you want to open the device configuration tool? Yeah, it's a good idea to do so. Okay. It will open, as you can see here, this .ioc file that will basically let you easily configure anything that you want to have enabled through a simple graphical interface. So we will start immediately with a very quick hello world project. And let's say that we might want to just turn on and off LED like this one. You can see that in this board specifically, and that will be pretty much the same on the others, The GPIO PA5 is directly connected to a small green LED that you cannot see here, of course. At the moment, it's not visible. When it will be on, eventually, you will be able to see that. Other things that are already set up is, by default, the Uart and an interrupt source. I mean, it is configurable as an interrupt source. In this moment, it's just input, digital input, this little blue button here. The black button actually is the reset button, okay? So you cannot use it as an other input source, but you can use it to reset everything. So it's another important functionality. Of course, if it's not working, that's like the Bill Gates method. It doesn't work, you reboot everything. Don't cite me on that. So here on the left side, you have a list, more detailed list of everything you can enable or disable if you wish. On analog, you have or your analog to digital converters, or your digital to analog converters, your comparators. You can have some operational amplifiers. Pretty cool, pretty cool, I would say. With these arrows you can close or open this side of the window. Here you have all your timers, all the timers. Here you have the connectivity based devices, let's say, all your Uart, Uart, the SPIs, and so on. Security devices, like here you have a true random number generator, and here you have cyclic redundancy check and other things that personally this I never used, so okay. Usually if you hover the mouse it should tell you the name. In this case, no, I guess. Fair enough. And other things also are available. Okay. In order to enable a specific GPIO, you just click on it here. If you know where it is wired. If you want to enable this, for instance, as in the digital input, you can just write GPIO input, click. If you want it to be an output, you can just do GPIO output. If you want it to be an external interrupt, this. If you want it to be put in analog mode, use GPIO analog. Actually, if you put it on analog mode, it can be a cool trick to save that little bit more of energy, because it will be placed in high impedance mode, meaning that if you have some voltage, it will, of course, the current will be lower, hence the power, so it's cool. Okay. Last thing that I want to touch here, is GPIO here. You can modify like directly in a more specific way all the GPIOs that you have enabled manually here. All the mode here. I guess for instance here analog mode you have to modify it here, of course, but you can choose a pull up and pull down resistor, for instance here. You can put a label, which you can do also with the right click here eventually if you want. And you can say you can enable the interrupts here also. On the NVIC section, you can enable or disable all the interrupt sources that are currently able to give you an interrupt, which could be the RCC, Uart. The XCL line 5210 is actually XCL line corresponding to the GPIOs. So, for instance, if I want to enable the interrupt from the blue push button, if you go under, if you click it, actually you can see that it's Gpio XTI13, so interrupt line 13. So you want to enable this button here. It says OK, line 15 to 10. And on RCC you have other mixed parameters. We will touch later this power regulator voltage scale, which is, as I said last time, it's the scaling of the internal voltage reference. You can, if you put 2, of course, it's a lower voltage value. That also means that, okay, one thing that maybe I failed to mention last time is that if you change the voltage here, of course, the lower it is, the voltage, so the scale goes in number up, the lower the maximum frequency we can achieve is. For instance, if I change it to 2, let's keep it to 1. Here I have a clock configuration, which lets me configure the clock for the main CPU and a lot of other peripherals. You can see that there are some peripherals that have the possibility of in which you have the possibility of choosing a clock specific to it. For instance, it's like this is the case of the low power Uart, the Uart 1, Uart 2, and the low power timer 1, and I think also 2, yes. You can see that here 80 megahertz is possible. If I want to change it to another value, I can adjust all the parameters here manually, or if I feel lucky, I can take the frequency value that I want to change, and I can just write the frequency I want. For instance, I can put 70, and it will try its best to reach a close enough value. You can see that it did actually. There is a configuration which I have 70 megahertz, which is cool. But you can see that actually I cannot always use this frequency, because if I change it to the scale to, no, it's not letting me, I guess. Wait. Okay, you could see before that when I had 80 here, it was still okay. It's still letting me put the scale to. If I go to clock, it says actually there is an issue. I think this is a temporary glitch of the software. But it's good practice to check everything every time, of course. If I clicked yes, so the software should have tried to change the configuration to something more reasonable, but of course it did not find that. What can we do at this point? We can do something, actually. If we just don't need this 80 megahertz because we want to have a low power thing, either way, we can just, for instance, lower it. If I change to MSI, you see that we went directly to 4 megahertz, which is this one. And if I go back, which is okay, it's fine for what we are going to do now. And if I go back on the pinout and configuration tab, you see there is no other error. Okay. Usually, one thing that could happen when you change the clock is that, especially for like something that you will find pretty much for sure, I think, is that on the connectivity tab, especially, if it's too low, the Uart, for instance, might not have a fast enough clock so it will not be able to work at this specific baud rate. So if I go like to 1 megahertz, there is an X here, and here it's saying that it's not possible, it must be maximum 65 kilobits per second, so it knows in this case. So if I change it, it will be fine, but I'm going to keep this value because it's the default one, and I don't care too much. We can put 4 megahertz. Okay, in order to, so now that we have everything compiled, only that we have chosen everything that we need. I mean, actually, we don't need this one, but we can keep it in this case. Like a small Gpio pet, I guess. We can generate the code needed for our application, for configuring the GPIOs and the other peripherals through this button here. Another way is to Control S, save this, and it will still ask you, do you want to generate code? In this case, let's use the proper way and press this button. It will ask if you want to open the C++ perspective, because it will throw you to the main.c file immediately after. You can I just say yes, because personally I prefer to watch the code immediately to see that it's good, but maybe you have different preferences. Okay, now we have a code that just configures the GPIOs and etc., but does nothing else basically. We can add something very fast, like an hello world. So for instance, excuse me, we might just do this. We might use the Uart to send a hello world message. So we can do like this, very fast. HAL. So I'm calling the hardware abstraction level libraries. You see that there are like two types of libraries here. You have the hardware abstraction level and the low level. I have not loaded the low level libraries. Of course, the idea is that on the HALs, you have an abstraction that is a little bit higher than the low level libraries, but they are more or less generic in a way that they should work with an L4 board, or if you just call the same HAL function, it will eventually work on a different microcontroller, always from the ST microelectronics. While for the low level, it might not be the case because they are more specific to the specific microcontroller. Okay, but of course you can achieve better performance ideally. My idea is that actually maybe it's good to work at least in the beginning with the HAL, and then eventually you can even move to the low level code, which will save you on this most critical tasks. In that case you can save a lot of time. But let's go step by step. Let's just call the library for sending a message through the Uart. In this case we have Uart. There is a transmit. Okay, and one thing you can do that I didn't mention or right now, you can type the beginning of your function and then press Ctrl and space to use the auto completion software, the auto completion feature of your ID of the CubeIDE, which is actually a base on Eclipse. It's based, this specific environment is based on Eclipse, of course. Okay, you can say that the function we want is actually the first one, Uart transmit. The other ones we might probably see the Uart IT later. Without might, we will. But for this example, I won't show this one. In this case, we can directly choose the pointer. Here it wants a pointer. You can see the star here. It wants a pointer to the structure that is used to govern the Uart2 in this case. Let's say to describe the Uart2. So you just put n Uart2. Here it wants a pointer again to your string basically that you are going to send. So we can just write like this. In this case we can use static definition, let's say. And you can see that it requires integer 8-bit integer, which is basically a char. So we can just write it like this: hello world. Maybe you can put backslash n backslash r to go on another line. Size, in this case, we can just copy this and do size of this small string here. The timeout is the maximum time that it is required for the transmission. Ideally, yeah, this is needed because if for some reason it hangs, the connection may hang, you are sure to at least go outside of this function in a reasonable enough time that you are setting here, of course. The timeout uses an internal reference that is based on the basically clock that goes on the microcontroller, on the CPU, and counts it ideally in milliseconds. So if I put 100, it means that if the transmission doesn't happen within 100 milliseconds, we are doomed. We need to stop. We need to see what is going on. Eventually, if you want to see whether or not we have an error, this function actually gives back a result. So you can put this in a if, like this, for instance, if I'll transmit is different than a certain value that you're going to see, we can say error. I don't know. You can go to, I think there is a function, error handler. Yeah, it was here also, I guess. Okay, what is this value? Ideally, if you have in these libraries, especially in the libraries, I mean, it is like common. It's commonly like in a common use, like people put some documentation nearby the function, so anybody that comes after can see, okay, this function does this, this, and this, and these are the inputs it expects, and these are the outputs that I expect. You can see that by clicking your function, usually, or hovering the mouse. You can see there is something. Okay, of course there is a syntax error, but it is, of course, I know this. You can press F2 usually to open the documentation in the. Sorry, let me put a value here so it doesn't give an error. If I press F2 or hover the mouse, you can see that this small window will appear within this file, so I don't have to open another file. It can be useful, and you can see that it sends an amount of data in blocking mode. When Uart parity is not enabled, then you want blah 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 blah. You can read it yourself. Let's go to the inputs. Uart handle, pointer to the data buffer, which is again the string in this case, amount of data to be sent, which is the size of, and timeout duration. Okay, when it will stop, you retrieve an HAL status. If you go here, you can see that actually it can return HAL error, and ideally, if it's okay, if everything is okay and the transmission went fine, it will return HAL OK. So, which is actually as value 0, actually is defined by value 0. In fact, if you hover the mouse, it will tell you 0. If you want to see where it is actually declared, the function or a variable or a definition, you can also press F3 and it will throw you directly on the file, specifically where it was defined, of course. Okay? So we have confirmed that it's actually 0. Good Lord, if it changed like this, it would have been like by magic, it would have been strange, I guess, no? Another way, extra way in which you can also access this information is by holding Control on the left control. I think the right control, also the right control works, and clicking on the variable or the function. So if I click here, it will go to the uart.c. If I click allocate, it will go exactly where we were before. If I click on error handler, it will go eventually down here. Okay. Now that we are sending this hello world, maybe let us explore like another very small thing. Control A, Control E will automatically indent everything. So basically, it will order the line, make the line of your code a little bit more readable, ideally, which is always good when you're speaking about code. So do it, because if I ever have to read your code and it is not well ordered, I will complain. Okay. We might, for instance, turn the LED on and off. One idea could be, okay. So we can wait a certain amount of time and do the blinking, okay. For instance, for that we could go in the while and say, okay, if I will write the code very fast, but it's not a problem, I hope. If HAL get tick, what is get tick is the internal reference I was speaking about before. You can see that also in the documentation. Provides a tick value in millisecond. The function is declared as weak, can be overwritten also, but you can see it just returns this value, UW tick, which is increased eventually in interrupt inside. You can find, I strongly advise you to read all the code that you have defined. Basically, it is called here in this case. But all right, so we can say that maybe we want to change it every 500 milliseconds. So for that we can use the %, which is the rest. We can write if I'll get tick rest 500 is 0, okay, means that 500 milliseconds pass. Every 500 milliseconds we can do all, calling now the other abstraction level libraries, but for the Gpio, okay, so we can toggle in this case the LED. Toggle pin Gpio, okay, in this case we need a port and we need your pin. So basically we are going here, you can see that Gpio X is the port. It can be, for instance, Gpio A, B, C, D, A to H and until Gpio H. The pin is the number of the pin basically. So for instance, if you go here, we see the LED is on PA5, means that it's on the GPIO port A, pin 5. Otherwise, when you make when you name them in the .iuc file, you can see that actually there are some custom definitions for that. In this case, we can see them on the main.h. They're declared there. We can access that with the Control tab. In the Control tab, we are going directly to the main.h. So basically to the .h file with the same name of that, of the file you're currently in. So if I do it also here, it will go back to the .c. So it's a quick way to access that. Usually it's good having the shortcuts, but of course you have to learn your shortcuts, of course. Okay, we can see here that LED two-pin GPIO 5, GPIO port A. Okay, we can just write it here, LD to GPIO port, and here LD to GPIO pin, LD2 pin, I guess. Okay. Now we can program our board, and we should receive a message through the Uart. That, how can we see that? Because you can see that, of course, the message will not pop on the screen automatically. We need a way to show that. And for that, there is a small terminal console that you can use. For that, you need to create a new command shell console. And, of course, it's a serial type of communication. You see, of course, you don't have everything filled up automatically. You need to create a new one, especially when you create, which is the case when you create a new workspace. If it's a workspace, old workspace that already contains a configuration, it will remain there. Okay, so you eventually, all the time, every time you open the program, you will not have to, of course, do this fresh. So let's call this, for instance, Nucleo. You can see in this case, I only have one COM port, which corresponds to this STM32. Eventually, to be sure, like if you want to know exactly, if you have several, don't want to try each of them, you can go here, Device Manager, and on the Device Manager, you can go inside Ports, COM ports, and it is ideally the one with STM microelectronics ST-Link. Okay. In fact, we are not connected to the Uart directly. Of course, it is the ST-Link that grabs the Uart signal from the UART2 by default and translates it in a way that your computer will be able to read. So we just say OK. Idea we should not. Oh yeah, spoiler. We can program our board, and we can do it with this button here, for instance, run. And it says there are no recent launches, but ideally it should work. Maybe not. Okay, you first have to click the. I know it's strange because it can seem strange, but you first have to click the source file when you're doing this. Okay, here, there I just clicked OK. Usually it is fine. It is the default settings for debugging are good. Eventually, if you are having problem, you will have to touch the settings yourself. There is, I think, some documentation on that, but here I did not have too many problems with that, so I guess. If we go on the on the console, you can see that we have our hello world. So we were successful in sending the hello world without problems, But is it actually toggling the Gpio, the pin, the LED? The answer is yes, actually. If I can keep, crap. If I can manage not to disturb this cable, it does it regularly. Okay? Which is cool. I think it's cool. Now let's look inside the debugging. For activating debugging, you need to click here instead, this small bug. And this is actually, of course, I showed it in the opposite way because ideally I wanted to show you that it works. Of course, I tried this before, and I knew it works, but let's apply a scientific method, of course. On the debugging, you will be able to see what your code is actually doing. So it is super, super important to know that. It is, I think, half of the work is knowing the documentation, and another half is using the debugger, and then another half, for 3 halves, of course, more than one, jokes aside, basically like knowing the documentation. Knowing is as much important as knowing as to program. It is as much important as knowing how to debug, because maybe your code will make sense, ideally, and will maybe work also on another machine. Maybe on your computer it is working, but it might not be the case. Specifically, maybe there is some glitch. I don't know. I'm just saying it could be anything, of course. We are speaking about lower level programming, so, and especially if you want to go on the super low level, if everything works flawlessly, you know there is a problem somewhere. Maybe you are sleeping, maybe, I don't know, maybe you're super lucky, but usually it's not the case. Okay, here you have that, let's go here, on the buttons you have here. You have buttons to skip the breakpoints, which, first of all, let's say what are breakpoints. While the code is running, you can put breakpoints that are points in which your code, basically the microcontroller will stop. It will stop to then give control to you and see what is going on. All the variables, you can have access to all the variables, all the registers, basically all of the registers, everything. You have access to everything, the memory, everything, all through these tabs here that we will show in a moment. And it is super important. It is super, super important that you know how to use it, okay? I cannot stress this enough. I'm sorry, I'm telling this a lot, but it is very important, okay? Okay, here you can go. You have the option of going over the function. So if I go into like step over, it will do the all init by itself. If I do it on the sysclock again, if I want to see what is going inside this function, because maybe there is a problem, a glitch, I can do step into, and it will go inside the function that it was overlaid and it was highlighted before. And here you can do again step by step, you can do step into again, or when we are satisfied in what you saw, you can do step out, step return. You can see on variables here, actually, that while you are inside the function, it will show you the variables that are currently used with the structures and everything. If you want to see in expression here, you can see also variable. You can put variables to see that if they exist, they will be shown. You can specifically do some operations here, which could be useful eventually. basically it could be useful to have access. Maybe you can do like if you have a number, you can multiply it by 2. I don't know. Or anything. You have a lot of freedom here. Same thing with the live expressions also, actually, but the difference is that while expressions and variables will only work when you are stopped, when the code is stopped, the live expression will always work. So you can monitor everything while the code is running, and you can even modify the value of some variables here. Okay, if I had a variable here, like Uart2, if you want to watch this on the live expression, I can directly access it here. This is, of course, it's not safe to do it, of course, but if in this specific for these specific variables, of course, but you know that it can be useful. Okay, if I wanted to go step out, to go outside, step return, I'm outside of the Gpio initialization. If I want to go even more deep, I can do an instruction stepping mode, and basically it will open the disassembly and it will show you everything, all the machine code that corresponds to what you're doing. So eventually you are also able to modify this code if you can identify again the most critical tasks. You might be able to do by hand optimization that will save you some time. Okay. Again, if we run, there was a breakpoint here. I guess let's put one here. Okay. Since the code found went here and there was the breakpoint, and now it stopped, and I can see what is going on also eventually. Okay, that's pretty much it. Last thing that I want to mention is that you have a way to here to show the registers, your internal register of your basically CPU here, more or less. And here on SFRs, you have the registers of all the registers basically. You have the registers on the DAC, where's the DAC, the E2C, and all the peripherals. Everything is here, and everything that you can modify with your line of code can be modified here also, ideally. Eventually, if I can find it. Eventually, there are some that you can modify, but I can, yeah, you just need to find it, yeah. Whatever. So that's it. And the very last thing here, you have to get acquainted with all the other. You should be able to get acquainted with all the other like tabs here. And another one that is important to know is the memory one. So here you can put a specific memory address, like for instance, I want to see this function here, what is in code. Maybe I can wait 80, okay, 0005, okay. If I go to 0x 0800051 here you are seeing the code that corresponds to this instruction, and probably more instructions actually, but you can even change this and cause stupid glitches, I guess. Yeah, exception. Okay, but ideally you can change this. Should be able to change the code here. Okay, that's it. Now we will move to the first example, and I will stop the recording for now.